Today we'll talk about um, these three algorithms: Ridge, Lasso, and ElasticNet. Okay, so though the names are different, they are same. Okay, the concept is same. Okay, concept is same of all the three. So when do we use this? When do we use this? This is a modification. Okay, this is a modification of our main regression that we did, that is simple regression. Okay, simple or multiple linear regression. So this is modification of linear regression. So what it says is, okay, when you have very less data, okay, now we've been talking about lakhs of rows, thousands of rows, right? It works well. Okay, any algorithm you take, it works well. But let's say if you have only few hundred, okay, then how do we do? That's what Ridge, Lasso, ElasticNet talks about. So what this algorithm says is, okay, that if you have less data, okay, so you know that your training model will not be good, right? When you have less data, so training model will work on the less data, and you know that it's not good, right? So introduce error. You introduce error. So same thing we discussed before when you are calculating standard deviation, let's say, for uh, population, and when you don't have population data, you have only sample data. So what do we do? Okay, um, um, when we calculate the variance, right? During variance, when we generally divide by n, right? In standard deviation formula, I mean variance formula, we divide by n. So instead of dividing by n, we divide by n minus 1. Why? Because we know that we don't have data for population, okay, and it is not going to be correct. So we are introducing error. Okay. So when you divide by n minus 1, what happens? Your variance or standard deviation increases, right? Error increases. So it's a artificial way of introducing error, right? Now let's say you predict a number 300, let's say, and you know that 300 is not possible because of whatever reason, but your prediction says 300. So you know that prediction probably is not going to be right. So you will not say 300, you will say 290 or 280, right? You are artificially introducing error because you know that your your analysis is wrong. So when you have less data, okay, for training, okay, you will not be, I mean, you will get error in your analysis. So Ridge, Lasso, ElasticNet is a way of adding error to it. Okay, how do we add this error, or what does it mean? Okay, so you see this data, right? Now, for simplicity's sake, okay, what we do, let's say you have only two data for training. You have only two data for training. So when you have two data for training, this model will fit perfectly, right? Left side. Let's say these red dots are training data. Okay, and you have only two data. It becomes easy to understand. Let's say if you only two data for training, then it will be a perfect regression line, isn't it? It will perfectly pass through. Line can easily pass through 2 points. So line will pass through 2 points and you'll get error as 0. Okay. So it will give you some m value and c value, right? Y equal to mx plus c. So you will get some m value and some c value. So what we are saying is, okay, we are saying that let's add some error to it. Let's not go with what model is giving us. So instead of this red line, okay, the Ridge, elastic, and all three are same. Okay, how much you add error is dictated by algorithm. So Ridge has its own formula, Lasso has its own formula. ElasticNet is combination, addition of summation of Ridge and Lasso. So, Ridge has its own way of adding formula, Lasso has its own way, and Elastic Net is when you add both the errors. Elastic Net plus, sorry, Ridge plus Lasso is Elastic Net. So if you add both the errors, it becomes Elastic Net. So there also you have option to try these three models and see which one is better. So what we are saying is, okay, and these are the green dots. Okay. Now green dots are your test data. Okay, that came later. So what we'll do is we will not, okay, even if you do the training here, we will not go with the red line. Instead, we will add the error and say, okay, instead of going with this red line, I will go with this black line as my regression line. Okay. Now you see, when you are adding error, okay, so let me take this and I'm going to put it in paint and delete this portion for a second. Okay, so you have your, based on weight, we are finding the height of a person, let's say. Okay, so based on weight, we are finding height. So this is weight and this is height. So you have two data point and this is what you made. Now I know that since I have only two or very few points for training, I'm going to add an error and instead of, okay, this is also red. Okay, instead of red, I will take this line as regression line. Now, when you add an error to it, this line will either be something like this, or error could be something like this also, right? Gray line. So we're seeing, okay, your model is giving me mx plus g, but I don't want to go with this m. Either I will increase the m value or decrease the m value. So in this case, which one do you think is better? Okay, okay, we know we have to introduce error. Okay, by how much? That's a different thing. But first, look at the direction. Should it be this? What do you call? Um, which color is this? Right? Should it be this color line or should it be this color line? What do you think? We know that we have to add error, right? Like in standard deviation, we know that we have to add error. Should it be n minus 1 or n plus 1? Should we decrease the variance or should we increase the variance? So the answer was increase the variance. When you increase the variance, that's when you can get more values into it. Now here, okay, should we decrease the m value or should we increase? Should we turn more towards x-axis or move towards y-axis? So answer is this one is a preferred method. Why? Okay, let's say you want to calculate m. Okay, this is the m. You calculate m, and this is the m. What is m value? How do you write m? Slope m equal to delta y by delta x, right? So let's say if this is x, okay, no, I mean, let's not use x and y. Let's say this is p, okay, this is p, okay. Now what happens? Let's say this is q and this is r. So, and let's say this is p. So if this is p value, if this is m, p, what will this be less than m, less than p or greater than p? Q will be less than p or greater than p. So as you go towards x-axis, you see the change in y value is getting smaller. See here, it is much bigger. So as you go towards x-axis downward, okay, as you go towards x-axis downward, your slope is decreasing because this y is getting smaller, right? Now, how do we read this? Okay, let's say if we have situation like 1 by 1, 2 by 1, or 0.5 by 1. Let's say we take these three slope values. If we take these slope values, what does this indicate? It indicates that if you change x by 1, your y is changing twice. Here it means if you change x by 1, your y is changing by once. If you change x by 1, your y is changing by 0.5. That means, let's see if this is weight versus height, okay? So if I increase the weight by 1 kg, the height will increase by 2 centimeter or 2 inch, whatever you call it, 2 centimeter, let's say. Here it means if the slope, if m you get is 1 by 1, that means if you increase weight by 1, your height is also increasing by 1 centimeter. Here, if you increase the weight by 1, your height is increasing 0.5 centimeters. Okay. So this is very sensitive. This becomes sensitive. That means small change in X will result in bigger change in Y. Small change in X will become bigger change in, very sensitive. Whether it increase or decrease. If you decrease by 1 also, it will decrease by 2. If you increase by 1 also, it will increase by 2. So this is how your R will behave. This is like your R, where the M is higher. This is like your P, and this is like your Q, right? So if you see, when you go towards Q, your M is decreasing. Okay, M is decreasing because the change in Y is reducing. So when you are not sure, and uh, okay, then in that case, this is a better choice than this. I know 1 by 1 is not true. I know 1 by 1 is not true. It has to be 0.5. I'm just giving number so that, it becomes easy to calculate. It has to be 0.5 by 1, like this one, or 2 by 1. This is preferred because here you are reducing the sensitivity, right? When you are not sure, you want to play safe, isn't it? When you are sure, then it's fine, okay? Then, this would be better. But because we have only very few data points to train the model, okay, we want to be safe with the model. So what happens? We prefer to reduce the M value, not increase the M value. Okay, so that's why what we do in the example here, okay? Okay, if the model is, if the linear model, okay, simple or multiple, whatever, is giving us this line, I will add error to it to bring it down, to reduce the M value. Did you understand? So the purpose of performing elastic net or Regression lasso is to 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 reduce the M value. Yes, to reduce the M value. That's the purpose of Regression lasso. Okay. Now, what is the difference between them? How are they different? Okay, so see, this is y equal to mx plus c. This is what is given to us by the linear regression model. So in Ridge, we are adding lambda into m square. Lambda is the error factor. Okay, and we have to choose the lambda value. So we are multiplying here the slope square by lambda. Here you are multiplying only power of m only. So if you see here in Ridge, we are adding more error. And in Lasso, we are adding lesser because m square, right? Here it's only m. So that is the difference between Ridge and Lasso. In Ridge, we add an error factor, which is lambda into m square. In Lasso, we add lambda into m. And in ElasticNet, let me see if ElasticNet. ElasticNet is both adding lambda into m square plus lambda into m. It must be somewhere here, okay? I must have written it here. Okay, so ElasticNet is sum of these two. Okay, so it's not there here, right? Ridge. So loss function is OLS. Okay, so lasso is this, and ElasticNet. Okay, so I have not written, but this is what ElasticNet means. ElasticNet is you add both the error factor. Okay, so it's going to be lambda into m square plus lambda into m. Okay, L and R. So now if you, ElasticNet is combination of both. Between L and R, okay, this is how I remember, okay? L comes before and R comes later, isn't it? Lasso L, ridge R. So lasso is lambda into M. Okay, power 1. M is power 1. R comes later, ridge. So
Lambda into m square.
M square. Okay. So this is if you get confused, like, oh, ElasticNet is big name, right? So it's combination of ridge and lasso, easy to remember. But between ridge and lasso, which is square, which is non-square. So whatever comes, lasso L comes first, so it is M. Okay. This is just for your remembrance. Okay. Nothing to do with actual values, but this is the actual formula for ridge lasso. But obviously, okay, we have Python, so we don't need to worry about the formula. Okay, linear model. So linear model only has simple linear. Okay, this one only. This also see. Okay, so linear model has linear regression, ridge, lasso, elastic net, all belongs to linear model. Okay, and we are using student scores multi-data here. So let me go back to PyCharm. Did you understand the concept, right? Why do we need to use ridge and lasso?
Yes.
Elastic net. Okay, what's the purpose?
Find the m.
Okay, when we have less number of data to train the model, we know that training will not happen perfectly. There will be some error in the training. Since we know there will be some error in the training, we artificially introduce error. So we introduce error using ridge lasso elastic net. Okay, and these are useful when you have very few data to test. Or I'm just trying to uh, get that data. So it's in data set. Okay, data set. And multi student scores multi. Okay, dot CSV. So I go to the raw version of it. Yeah, it's working now. So I'll copy this link and come to our PyCharm. Okay. Done. Now here, okay, you see, you can directly read. So df equal to pd dot read CSV, and we give link. And if you want to see the data, we'll say df. Okay. So it's pointing to different file. Okay. So you have data like study hours, play hours, and watch TV, right? So it's again like predicting marks for students based on 3 activities. So you have 3 features here: number of hours they study, number of hours they play, and number of hours they watch TV. Okay, and this is the marks. This is what we want to predict. Okay, so this is the data set. Now, what I'll do is we will break it into X and Y. Okay, no categorical and no missing value, no scaling required, right? So we can directly go ahead with model building. So X equal to your data df dot ilog, okay, all rows and 0, 1, 2, right? Columns. So I'll say 0 to 3 columns dot values. 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 0 to 3 columns dot Now I'll go copy and I'll say y, and our fourth column is y, correct? Okay. Now we will break it into training set and test set. So we'll say x train, comma, x test, comma, y train, comma, y test. Okay. Okay. We need to import it first, isn't it? So from sklearn dot model selection, import train test split. Okay. So this is equal to train test split and x comma y. And now instead of giving 20% as test size, I'm going to give 80% as test size or 85% as test size. So that means even though we have some 30 rows here, right? Okay, 30 or 31 rows we have, 32 rows we have, right? 0 to 31, 32 rows we have. We will give only 5 or 6 to the training. Okay, so we will train on 5, 6 rows. Okay, 15%, right? So 15 into 3, correct? So we will get about, yeah, 5 rows will be for training, and then we will test it on 25 rows, isn't it? So obviously there will be error. Okay, so that's why we'll say 85%. And let's have random state equal to 100. Okay, so this is ready. Now let's build the model. Okay, so to build the model, how do we do? We have to say from sklearn, okay, dot linear model import. We'll import linear regression, we'll import ridge, we'll import lasso, we will import ElasticNet. Okay, so we'll import all the 4 algorithms. Now I'm going to show you one, and you have to do it for rest of the 3. Yes. Okay. So now I'm sure you must be very familiar with building the model now, right? Okay. Call whichever model you want to call. Okay. Then create an object. So I'm going to say linear regression ridge. Okay. So you put R for ridge, or I can put ridge here, or L for lasso, E for ElasticNet, and LR for linear regression. So I'm going to say linear regression ridge equal to ridge. Okay. And do we have to provide anything else here? The error alpha value. Okay. So I'm providing alpha value with, let's say, 0.5. Now I don't know what is the best alpha value here. Correct? You have to run a loop. Okay, you have to run a loop to find out. How do you find out? From the beginning, you can start from 0.1 to 1 or 0 to 1, right? You can say alpha equal to, if I say alpha equal to 0, it is same as linear regression. Okay, alpha equal to 0 means same as linear regression, no error, right? Mx plus c plus 0 into m, 0 into m, okay, or ridge, right? 0 into m square. So 0 into anything is 0 only. So when I say alpha equal to 0, it is same as a linear regression. So you can take for loop, you can have, you can give value from 0 to 1 with gap up, step of 0.1. So it will be 0 first, then 0.1, 0.2, 0.3, 0.4. Based on that, you select the range which you think is the good range. And then there you can again go with another for loop where this time you'll go at 0.05, right? But you'll probably get that, okay, value somewhere around, let's say, 0.6. So between 0.5 and 0.4, you will go at 0.05 step. That's why you have to run it multiple times to figure out what is the right alpha value for this problem, right? So, okay, for demonstration purpose, let's say I take alpha equal to 0.5. Okay, so this is done. What's the next step? What should I do now? Guys are not awake, still sleeping. Okay, fit, and I will fit it on training data and X train and Y train. Okay, now you predict on. So I'm going to say Y ridge spread. Okay, you'll have similarly prediction for ElasticNet and this. So you'll say spread, and this will be your LR ridge dot predict. Okay, your X test, right? And then you compare, calculate RMSE and R square, okay, for both training data and the test data. So I'm going to say I'll calculate R square only. So I'm going to say from, right? Okay. From where do I get the metric? Which model should I call? Where are your metric? sklearn dot metrics. Okay. And let me import R square. Okay. I'll just use R square. I want you to do for RMSE also. Okay. So R square. Now, how do you calculate R square? So I'm going to say R square. Here, this is ridge. And we will have for train, and later we'll calculate for test also. So if I have to calculate for train, how do I calculate for train? R square. Okay. And what do I put here in R square? This is train, right? So I'll first put X train. Now, before putting X train, I need to predict this model on X train, right? So I'll say Y ridge spread train, okay, equal to Y ridge spread, Y ridge spread is not required. So predict on X train, right? And this will be your predicted value, okay? X, Y train is the actual value, and this is your predicted value, right? So this is how you build your what we call as training R square, training accuracy. Yes. So this is your training accuracy. Yes, with me. Or did I make any mistake here? All right. Now, okay. So similarly, I have to say, okay, R square ridge test. R square ridge test equal to your R square. Okay. And here I will pass Y test and the predicted value from X test. Okay. Now let's print both these values. So I'm going to say print regression F here your test or train. First we'll print train. Train R2 equal to this and test R2 equal to this. So train is R square is this one and test is this one. Okay, so let's run this and see. Okay, so you see here, your training is 0.88 and for test it is 0.12, right? probably, first let me see if I got the value right. This is training, right? Okay. On training, what I'm doing, so I'm taking Y test and the spread is on X test. Okay. So raise test. And this is training. Okay. Train and your train. Now you see, okay. Now the difference between test and train is very high. What does it mean? We are into overfitting area, right? So we need to adjust the alpha value. Okay. We need to probably introduce more error or less error depending upon the value. Okay. Okay. So now you see it has become bad. So when I decrease it, it became bad. So I need to increase it. So let me make it 0.8 and then you see what happens. Okay. It improved slightly, right? So maybe this problem is probably not better with Ridge. It could be better with ElasticNet maybe, right? So this is how you have to change the values and calculate your thing. So what I want you to do is create an Excel document. Let's move on to our notes here. Okay. So I just did Ridge now, right? I just did Ridge now. You have to do for Lasso and ElasticNet. Okay. Same thing you have to do. Now, okay. Calculate for Bridge, Lasso, and ElasticNet. Okay. And create a Excel table like this. Okay. So if you see here, obviously because we have very less data, right? Where we have very less data for training, accuracy will be very high. Linear is giving you 100%. Reason Lasso, at least there is some error. Now in 0.8, our training data became 85%. So we are adding error, okay? We are adding error so that test data improves, right? So this is what I calculated using the code which is here. So you can see with just 0.1% error, okay, it improved by almost 10% here, test data. Okay. So this is how you can manage when you have very few data to train. So will you do it for Lasso and ElasticNet also? Same thing. So what I did for Range, you have to do same thing for ElasticNet and Lasso. All right? With me? What happens?
Yes, sir.
Yes. Thank you. Then with that, we complete our regression. Okay, we will do a few more regression towards the end. After we do classification, we'll come back to regression because we'll talk about their bagging, boosting, and ensemble. Then we will again come back to regression. So then apart from that, you have to understand what is overfitting, what is underfitting. We have already discussed this, right? So what is bias, what is variance? Okay, very important concept, very popular in interview. Okay, so overfitting, underfitting, bias, variance. Okay, you have to understand. Then what is R square, adjusted R square, right? So these are the things. And this is the summary. You can read it. Okay. Model selection in regression. This is like model selection regression. So no option, but you have to run all the model and check for the value, whichever is better. So here you see this example uses linear regression, raise, lasso, elastic net, K neighbors regressor, decision tree, random forest, SVR. All this I have to run all these model on the data because you don't know which model will work better on the given data. So you have to run all the model, you have to evaluate all the model, and then you figure out based on R square and RMSE which is working better. Okay, so Lasso ElasticNet regression is part of linear model. Your k-neighbors regressor is part of neighbors, and this is again again a classification example which has been modified. So we'll discuss more about this in classification. Then decision tree is part of tree. SVR is part of SVM, support vector machine. Random forest is part of ensemble. Ensemble is where you learn multiple times same type of model and then you get the average of the values. Okay, so these are the models that we have discussed so far. There are many models even in machine learning. Okay, so of course more you practice, more you learn. See, in machine learning, I'll tell you concept wise, very simple concept, yes, but your experience will show when you speak about it. The more you practice, more you do, more understanding you will get about this topic. Okay, and when in the interview, if they ask you questions, your experience will show up the way you answer. Okay, if you do only one problem, okay, your answer will be different. The way you answer will be different. If you do 10 different problems, the way you answer will be different. So at least you need to practice 10 different data. I'll give you, towards then I'll give you some examples to practice. Okay, and I'll also talk about various sources on the last day, various sources from where you can practice even more problems. Okay, so what are the metric that we use to measure accuracy of regression models? What are the metrics that we use to measure the accuracy of regression models?
R square RMSC.
R square, RMSE. Okay, so RMSE, so MSE is also part of it, right? Yeah, okay. So yes, MSE, then MAE, right? Mean absolute error. Okay. So yes, so these are the metric that you need to use to test or evaluate the performance of your regression model. All right. Next, let's talk about classification. Let's just talk about what classification is. And we will start with our models tomorrow. Right? So what is classification? What is regression? Like, let's talk about regression only. What is regression? Okay. So understand, okay, regression is, okay, this first fill in the blanks and second fill in the blanks. Okay. In the first fill in the blanks, you talk about whether supervised or unsupervised. Is it supervised or unsupervised?
Supervised.
Supervised, yes. So regression is a supervised algorithm. Okay, or regression is a family of supervised algorithms which is used to predict what kind of target values? Numeric, right? Numeric kind of values. So now this is for regression. Now, if I have to ask you what is classification, then this part is same. Here you will say which is used to predict multiple
Category.
classes. Sorry, categorical value or classes. Yes. So you are predicting the which class it will belong, right? Yes, no, okay, or A, B, C. Okay. So you are predicting which class so here also you will have X features, multiple features. Okay. And okay, based on this, it will tell you which class it belongs. Now, if you talk about accuracy model, okay, accuracy of classification model, we cannot use MSE. We cannot use RMSE or even for that matter R square. Why? Because these are not numbers. Now, if you see, these are all about, okay, like actual minus predicted. Here, let's say actual is yes, and it could be yes, or actual is yes, it could be no, right? Or actual is no, it could be yes. If actual is no, it could be no, right? So how will you minus? You can't minus. So these metric cannot be used for classification. Classification, if you see, okay, when you have two classes, yes, no kind of prediction, you need to draw a 2 by 2 matrix. Okay, to evaluate classification models, we need to use 2 by 2 matrix. Now let's say this side we put actual, and this is, let's say, our predicted. Okay, now so actual could be yes, or we'll start with no here. No, no, yes, and yes. So this means how many are actually no and you predicted no. This is, your model has got it right. Actual no, but you got it yes. So this is wrong prediction, isn't it? Then you talk about actual yes, but you predicted no. This is also wrong classification, right? Wrong prediction or wrong classification. Then again you have yes, yes, right? That means actually it is yes and you predicted yes, right? So you will end up getting 4 different values. Okay, not 1 but 4. Okay, so no, no, yes, yes. These are correct prediction. Actually it is yes, okay, and you predicted yes. Actually it is no, and you predicted no. But these two are your errors. NY, YN. Okay. So there are various metrics like you have accuracy, misclassification, sensitivity, recall metric. All those things are calculated based on these 4 values. So we only deal with these 4. How many? I mean, these are all numbers, like how many? How many actual value, which was no, you predicted no. Actual value, how many? Actual value, yes, and you predicted yes, right? So these are your correct values. Then how many wrongly you classified, right? So, okay, so this is again different, but pre-processing steps are exactly same. Missing value, standard scaling, which is done at the last, your categorical value conversion, your what else? Right? So pre-processing steps are exactly same. Again, running the model, you will not have any problem. Same 3 lines, and then model evaluation. Okay. What we need to understand is the working of different algorithms, how SVC works. Okay. Okay. So SVC is a classifier which is modified to make prediction in SVR regression. Similarly, we have linear regression model, which is, we call it a linear regression model, which is converted into classification. Okay. So, so we have a model which is actually works like regression model, but this has been modified to work like a classification. It's called logistic regression. So logistic regression is a linear model modified to work in classification. SVR is actually a classification model which is modified to work as a regression model, right? Concept is same. We will talk about those things in the next session. Any question before we wrap up?